Any questions before we start? Okay, question about course 1. Yep. So the audience is first-year computer science students. That's the audience. So not very much knowledge. Yeah, but as if they were in their first year of computer science. Yeah. Just to try, are you a first year computer science student now? So imagine you have to give a presentation in front of this audience. Yeah. Yep. Any other questions? Okay, so today we're going to talk about data visualization. Does everybody remember this slide from 1 week ago? It would be hard to remember. But anyways, I showed you this slide 1 week ago. I have a recording in case you're not sure. And it mentions this word visualization. So visualization is one of those tools that you can use to try to convince somebody that what you've done is in line with your goals or your hypothesis or your analysis and so on. Right? It makes sense, right? Data is much more useful if we can see it. So data visualization makes data visible. Otherwise, it might be invisible. And if you think about it, most data is actually invisible. So visualization takes the data and makes it visible, and it hopefully does it in some way that makes sense. So we're going to talk a little bit about information visualization. So this is the visualization of abstract data. So data that does not necessarily have a special position in space or a special position in time. But this is like going back to the origins of data visualization. Florence Nightingale, she used data visualization to try to guide some of the policies of the British Army, right? So what she did was she mapped deaths to both time and quantity, right? So this is the number of, both of these represent the number of deaths that occur in the British Army. So blue is mapped to the percentage of deaths that occur due to preventable diseases. So these are people in the Army that are dying, but their deaths could be prevented simply by treating the disease, right? And these are the number of soldiers dying from wounds, and then black is mapped to all other causes. And so what she was able to convey from this diagram is that actually most of the soldiers were dying not from war directly, but from preventable diseases. So that's something they have control over, right? That's something that they can actually prevent. And she also cleverly mapped the number of deaths to the months of the year. So for example, here in June, there were almost no deaths due to disease. In May, right? In April, May, June, and then July, these start to increase. And you can see here the greatest number of deaths due to preventable causes was in the winter months, right? So she was able to use this data, categorize the deaths, map them to time and space to actually influence policy in the British Army. This is a very, very, one of the earliest known examples of information visualization. And for a lot of these, I show a lot of examples in this lecture, and so I don't go into a lot of detail, but for all of the examples, I've put a link in case you're interested to see more details. Visualization is a big topic. It's its own, again, it's its own module. You can take a module. Is anybody taking the information visualization module, by the way? It's its own module, right? You can take a scientific visualization module, information visualization module, medical visualization. So it's really its own subject. We just provide a kind of introduction in this lecture. So the human visual system is the most powerful of the senses. The greatest amount of the brain is dedicated to the human visual system, right? Something around 1/3 of the brain is dedicated to the visual system. And that's very large compared to the other senses. It's only about 8% dedicated to processing auditory information, and less than 5% for things like smell and taste. So the human visual system is very, very good at identifying groups, borders, paths, patterns, making judgments based on size and length and height. Visualization can be used to explore and search data very quickly, analyze data, communicate it with a wider audience, and also verify the correctness of data generation and data collection processes. Right? And if you can verify that what you're doing is correct in your data collection process, you also build confidence in what you're doing that's correct. And the information visualization consists of these general steps, right? These are data-centric steps of collecting and generating data. Then there may be some data processing, like filling in missing values or correcting errors or interpolation. And then we have mapping that data to visual primitives, things like lines, colors, points, triangles, squares, rectangles, polygons, textures, and so on, or maybe transparency. And then finally, we render the data to the screen using some computer graphics techniques. And then finally, we look at it ourselves, and we interpret it with our brains. That's the basic process that information visualization takes us through. And there's something missing here, and that's interaction. So imagine I'm looking at an image and I want to modify the parameters of the image. I can interact with it, and we'll show examples of that. And then the whole process gets updated in this kind of looping fashion. Anybody recognize this one? Anyone seen this one before? This is quite a famous data visualization. It's famous for a few reasons. One is it's very old. It's one of the early information visualizations. Another reason is it's multivariate. So you can see multiple aspects and dimensions and characteristics occurring at the same time. It's called Napoleon's March, the Napoleon's March to Moscow, Napoleon's Army. So it starts out in France. The width of this arc is measured by, it reflects the number of soldiers in the army, in the French army. And then the x-axis is mapped to time. So we go from left to right as time goes on in the army marches to Moscow. You can notice that the army is getting smaller over time. Right, and finally it reaches Moscow, and then they return, right, back in time, and you can see the size of the number of, well, you can see the relative proportion of survivors that survived that journey. There's also temperature mapped in there. You can see there's a temperature being mapped here along the x-axis, like -11, right? -21, like there's some very, very cold temperatures in there. So that's one of the variants. So you have things like direction, the size of the army, the temperature, and the time all mapped into one visual image. Right? It's quite a famous one. It's written in French, by the way, just to make it more difficult for you to read it. Any French scholars in the room? This is quite a famous one. You can find lots of information about this. By the way, there's no link. I didn't put a link in this one. Does anybody know how you'd find out about this if you wanted to find out more? Anybody? No? Nobody knows? Does everybody know about Google image search? Okay, so you can pop this image into Google image search and then get more information. It's a very nice feature. It's really, really, really good feature. I use it to track down fake accounts, fake Facebook accounts and fake, other accounts by copying and pasting those fake profile images into Google image search. Some of the so-called visual variables that can be used to communicate information, right? We can map data to position. So we just saw in that example, data was being mapped to position. Data was being mapped to size, the width of that band that represented the trajectory of Napoleon's army. We can map data to brightness, from light to dark or dark to light. We can map data to color. Orientation, so orientation is an angle, essentially, like in a pie chart. And texture, so we can use different textures to map data, to represent data. We can use area, volume. Volume is three-dimensional, right? Area plus depth, and then shape. So arbitrary polygons like triangles, squares, rectangles, pentagons, octagons, and so on. So there are lots of different options. So here's a little kind of comparison. Imagine we have two test scores. Ann scores 100 and Bert scores 50, and we want to compare those. We want to map that data to something visual. We could map it to area. This area is twice the area of this one. This size or height is twice this one. And this one is twice the darkness as this one. Which one of these is the best? Anybody have any opinions about which one is the best choice? Yeah, the second one in this case. Very good, very good. So there are lots of decisions to make when you're designing your visual analysis. You have to make lots of decisions. Which data maps best to which kind of option? So here's another example of a 7-inch pizza and a 10-inch pizza, but the surface area is actually double, right? It doesn't look like it, but the surface area is double. Here's another example of pie charts are super popular, right? They're very, very popular. You see them all the time. And they are useful, but then the question is which one's more useful, right? If we have if we take a poll of people and say, what's your favorite social media channel? We can map that data to a pie chart or a bar chart. And then the question is which one's more effective. And I think that would be the basis of a very good user study. Right? You could make a user study and test people, right? Ask these questions and measure their accuracy and response time to find out some objective data to support your hypothesis, right? And here's another example of pie charts versus stacked bar charts. In this case, we have 3 pie charts, right, changing from year to year. And we have the same information represented with stacked bar charts from year to year, right? And which one is better, right? That would also be a good user study to make a user study to try to actually ask people not only their opinion, but ask them to perform a task to say something like, how much did materials cost in the year 2012? Right? You can ask people, how much did materials cost in the year 2012? You can ask the question showing the pie charts, or ask the same question showing the stacked bar charts, and see which one they get correct more often, or see which one they get correct more quickly, right, to find out which one is better. This is not the world's fairest comparison. I mean, if you look at it, there are labels here on the pie chart, but it would be a little bit more fair, I think, if the labels were actually on the stacked bar chart, but they're over on the side. So there are these small differences, but very subtle differences, and all of these differences factor into how effective the visual design is. Here's another one. This one is very intuitive because it's talking about land mass, right? How much farming area do you need to produce different outputs? The most farming area here is used to produce things like beef and other meats, right? And far less land is used to produce vegetables, right? Grains and vegetables. So that's an intuitive use of pie charts, right? This is a fancy pie chart. This is also called an infographic, right? It's a graphic that shows you information. We're not going to talk very much about infographics. And you can consult visualization guidelines. So if you're not sure, if you have some data and you want to represent it visually and you're not sure how, there are guidelines. Right, here are some guidelines. For example, shape could be mapped to points, lines, areas, and it's best to use shape when you have qualitative differences. Right, size can also be used to map to data, right? And lines can change their thickness. And these are cartograms. Does anybody know what a cartogram is? Anyone? It's a map. Right. So these can also be shown to quantitative differences, right? Qualitative versus quantitative. So you can actually represent data a little bit more accurately with size. Right? Color can be used to map to data to show qualitative differences. For example, when we say qualitative, we mean two different categories. Like maybe one category is better than another, or warmer or colder than another. This is color value, so color intensity and texture. This is an example of texture. You might have been wondering what does texture look like for data visualization? And this is an example. You can texture points or ellipses. You can texture lines, and you can texture areas to show qualitative and quantitative differences. I'm going a little bit fast because we're just really providing an overview. At the end of the lecture, I show you more information about where you can get more information on this topic if you want to go into it a little bit deeper. So we have this feature of our visual system called pre-attentive processing. So when we see something, our visual system can make some judgments very quickly in less than a half of a second before we've even had the time to think about it, actually think about it consciously. That's called pre-attentive processing, the subconscious accumulation of information, or being able to perceive things before we're even really aware that we can perceive those things. For example, size, orientation, color, curvature, motion, and shape. In other words, if I showed you this image imagine I showed you this image for 3/10 of a second, so it just flashed in front of you and disappeared again. This is I won't be able to do this experiment right now, but if I was super prepared, I could do it in front of you right now. Imagine I show you that image for 3/10 of a second, you just see it as a flash and then it disappears. And then I asked you, were all the heights the same or not? True or false, all the heights are the same. You'd be able to answer false even though you saw the image for less than a second or less than a half of a second. Your visual system works so fast at that kind of task that you don't have to think about it. And it's the same with orientation, color, curvature, motion, and shape. Right? There's a kind of quiz that helps explain it. Right? If I ask you where the 3s are, it's difficult to, there's no pre-attentive processing in this image. You can't use pre-attentive processing to identify the 3s in this image. You have to look at every number and see, oh, there's a 3. Here we can actually use pre-attentive processing, right? The color is a pre-attentively processed encoding. And then here, size can also be used, right? It's not as easy with the size. The color is the easiest. So people perceive, the visual system associates data based on different characteristics. So for example, proximity, the human visual system will automatically associate those 4 ellipses with each other just because they're close to each other. The human visual system will also group data and shapes based on similarity. Closure, right? Closure is something the human visual system will interpret and perceive. Symmetry, motion. This motion is not showing up on the PDF, but that's why I have the PowerPoint. Let's see if it shows up here, because it is cool. Yeah, that's pretty cool. Right, those are, if you look at it carefully, those points are actually separate. Oh, that's not very nice. Those are separate points, but because they're moving together, the human visual system connects them together, right? Continuity is an association, right? And past experience, right? So our visual system has a lot of complicated processing, and we don't even understand how all of the properties of the human visual system because it's so complicated. Right? In data visualization, we're always using color. Right? Most of our images have color nowadays because we're using color to communicate some information. And color is defined as a wavelength. But when we use data visualization in practice, we are aware that every device has its own range of colors. Right? There's a special range of colors for the monitor on my laptop. There's a different range of colors that the projector is able to project onto the display. Right, and those sets of colors are usually depicted on this so-called color space with a band around it that says, okay, like the projector can handle this many colors, the laptop display can handle this many colors, and so on. And that's why, like, when you print something out in color, it looks different, right? Because the printers have a different set of colors that they can handle than the screens that you're looking at. A lot of people are colorblind, so this is one of the statistics in the UK. Right? 8% of males have some sort of color blindness, and 1% of females have some sort of color blindness. You can actually design images that are so-called colorblind safe. right? There's this tool called Color Brewer that actually lets you choose colors and then design colorblind safe colors. So there's this option here, show only colorblind safe patterns, right? So these are actually colorblind safe patterns, the ones that we're looking at right now. Here's a kind of simulation of color blindness. Right? If you're colorblind, you won't be able to appreciate the simulation. Anybody here colorblind? By the way, like there are different kinds of color blindness. Some people can't perceive just, for example, red and green. They just get those two colors confused. And there are different pairs of colors that people get confused. So it can be like a partial color blindness, not a full color blindness. And these are some of the different color blindness, right? So here, like the red has kind of disappeared and turned into brown or something. The orange has changed, but the yellow is still there, and the green has changed. Here, the reds and greens have disappeared completely, right? The reds, greens. And here, the reds are still here, but the greens have disappeared and the yellow has disappeared. At least that's the way I see it. I don't know if that's how everybody else sees it. Gesundheit. And you all know this already, but we have lots and lots of different kinds of data. Categorical data is things like good, bad, medium, or like top, bottom, middle, like strongly disagree, strongly agree, neutral, those sorts of categories, first, second, third. We have numerical data, that's the data always expressed by numbers, like temperatures, and pressures, and time. We also have multivariate data, so that's more than one category or more than one dimension together. So for example, if I'm doing an experiment, I might measure heart rate and blood pressure at the same time, or heart rate, blood pressure, and temperature, body temperature at the same time. That's multivariate data. Geographical data is data that has a position in space on a map. We have temporal data, so that's data mapped to time, and then we have relational data, data that depicts implicit or explicit relationships. So, for example, in a hierarchy, a management hierarchy, or something like that, or a graph where nodes are connected to each other, like the subway, for example. So categorical data is items that might not be ordered, right? But they're in some sort of a group. Someone could be working full-time, part-time, unemployed, studying, or retired, right? The categories might have values associated with them. Like ordinal data is like first, second, third, fourth, and fifth, for example. We might group data into buckets like we do with the scores of exams, right? Like first class, second class, third class, and so on. Age groups are a common example. Grouping ages by into intervals like 5-year intervals is very common, right? 0 to 5, 6 to 10, and so on. And here are some traditional visualization methods for categorical data. These are the ones you're very familiar with, right? The bar chart and the pie chart. I'm not going to spend a lot of time talking about those. Here's an example of numerical data, right? This, the value of the riot stock on a daily basis, right? This is also temporal visualization. So here, time is mapped to the x-axis, and then trade value is, trading price is mapped to the y-axis, right? So the best time to buy this stock would be right here. That's from seekingalpha.com if anybody's interested. Box plots are very common for showing kinds of ranges instead of just exact values, right? They show the median value, the upper third quartile, another third quartile, the minimum value, right? That is not an outlier, and the maximum value that is not an outlier. So usually they show some distribution information, right? How the data is distributed. For example, the ages of heads of governments around the world. So here we have in Africa a very wide spread, right, from 45 to 90. In Asia we have again 45 to 80, and so on. Europe, you can see there's the youngest set of heads of government. North America is more compressed, and so on. On the left, we have a scatter plot. So that's when we have two axes, an x-axis and a y-axis, and every data point has a position in that space, right? That's what a scatter plot. This is an example of a scatter plot that's overplotted. So that means there are data points plotted on top of each other. It's very crowded. And this is the same scatter plot, but using clustering. So data points that have been with similar characteristics have been clustered together, right? Those are called multivariate data glyphs. And there's a video you can have a look at if you're interested in that in action. We won't look at the whole thing, but it could be fun to just look at it for a few seconds. So the data in this case is actually agents in a call center. So how do you visualize the behavior of thousands of agents inside a call center, right? This is a scatter plot example. And every one of these points represents an agent in a call center, right? And we can look at the multivariate data using this so-called scatter plot matrix. So every rectangle here is a scatter plot, actually. And if we align them all, they're scatter plot matrices. They're colored by the department they work in, right? So some of them work in collections, some of them work in retention, some of them work in credit department, customer services, the billing, sales, tech support, and so on. So you can see which department they work in based on their color. So we won't get into too many details, but this just goes to show you scatter plots, their interaction. You can have interaction with these scatter plots, right? You can change the visualization parameters. You can change the axes to show different properties. You can cluster those points together if you want to. You can look at multivariate data on those for those agents and so on. So multivariate data is data arising from more than one variable. So when we try to combine different dimensions together, like age, gender, height, into one visual representation. That's what those glyphs were on the previous slide. This is multivariate data here, trying to map several characteristics or data dimensions onto one visual image, one visual symbol. We can use multiple bars and bar charts. We can use so-called radar diagrams and parallel coordinates. These are all multivariate visualization techniques. This gets into some more advanced visual representations. Interaction can help enable extra information about the data to be known by hovering over data points. right? And the tasks that are used to analyze and explore this data depend on the context. You know, what are the questions and the hypotheses you're trying to answer or address? Here's just an example of a multivariate data technique. This is a common question that comes up in pubs and bars, right? When guys go drinking and they're like, "What's the toughest sport?" They always get into this conversation. What's tougher, like American football or rugby? Has anybody heard that conversation before? That's very, very common, that one. Anyways, here are some scientists that actually tried to answer this question in an objective way, and they visualized the multivariate data using this radar chart. So they asked sports scientists to rank a bunch of sports based on these characteristics, like agility, analytical aptitude, durability, endurance, flexibility, hand-eye coordination, nerve power, speed, and strength. So they ranked, for example, every one of these polygons is mapped to one sport, right? And the bigger the polygon is, the greater that dimension is. So for example, this is the sport here that requires the fastest speed, right? And whatever sport is represented by this polygon in the middle is probably the least toughest sport, so to speak, yeah? And they found out, like, according to their analysis, anybody know what the toughest sport is? According to this article, it's boxing, which I can, you know, that seems like a good answer to me, actually. I wouldn't want to do boxing myself. Parallel coordinates are another kind of multivariate visualization technique. It's okay if I'm speaking a little bit fast and not everything makes sense. You have the chance to look at some of these things in more detail if I leave out some of the details. But here, every dimension is represented by an axis, right? In this one, this happens to be a data set about cars. And when you're shopping for a new car, you think about different characteristics of the car. You think about, okay, there's a price. You think about how efficient it is, like how many miles per gallon or whatever, miles per liter or kilometers per liter it can travel. You think about the color. You might think about, does anybody here think about engine size? You might not think about engine size, some people do, but you might think about the weight. Like, do I want to buy a heavy car or a light car and so on? So that's what this data set is about. It shows the number of cylinders for each car, the amount of, the engine size, the weight, the power, how fast it can accelerate, the efficiency, and the year it was made. And every car is mapped to this polyline. So one car gets its own polyline that indicates the values of each of these attributes. Right, and when you visualize a collection of cars, it looks like this. Now, to decipher the individual cars, you'd need to apply interaction, right? So you could, for example, click on this polyline, and it would highlight the values along that polyline for an individual car, right? But I can see some patterns, right? For example, I see here there's a group of cars with 8 cylinders. There's a group of cars with 4 cylinders, and there's a group of cars with, oh no, that's 6 actually, 6 and then 4. And then there are some outliers, some very strange, unusual cars that don't fall into this pattern, right? So, if I'm looking for efficient cars, right, I would look up here. And I would be thinking, okay, I want to see which car that is. So I click on the polyline, or I brush this axis to find out what are those most efficient cars. Anybody know what they are? Anybody have experience what those efficient cars are? This data is old, actually, so my knowledge is getting outdated, but it's usually the Japanese cars that are in there. So we also have another category called geographical visualization or geovisualization. So we represent geospatial data. It's usually on a map, right? And there are lots of special tools for this kind of data. And that's usually when you're trying to study something to do with demographics. For example, like where in the UK is the population the oldest, the average age the oldest? Or where in the UK is the highest percentage of cancer rates? So you want to see that on a map, generally speaking. Right? Here's an example. Where do people kill each other in Washington, D.C.? Right? And you can see this on a map. And these are points, but there's also kind of a density here. So these are the locations of homicides, but these are also using a kind of density information. So the more dense the numbers are, the more red they are. Right? Here's another one where we're placing pie charts or multivariate glyphs on a map. Right? If we try to use a naive algorithm, the pie charts might overlap. So we might try to come up with some algorithm to place the pie charts in a kind of logical way so that they're not overlapping so much. And we can have a quick look at that one too. This is a kind of interactive visualization techniques. So we can zoom and translate the map. So there are the pie charts being placed on the map, and they're being clustered together, right? If they start to overlap, then they get clustered together in an interactive way, right? So as we zoom in, the map gets bigger, it occupies more screen space, and then we have the opportunity to introduce more glyphs in more detail into the map. Right? So that's a kind of geospatial visualization. And temporal data is any data that's mapped to time. This is not surprisingly very, very common. I mean, all data is associated with some time, but this is data that's changing over time, right? So we're measuring some value continuously or at discrete intervals over some special time period, right? That was the Napoleon's march to Moscow was one of the examples. The Florence of Nightingale example was temporal visualization. Right, this is an example of a scatter plot, right, where the x-axis is mapped to time. And this is the call center example, right? So every data point here represents an agent or a customer talking to each other in a call center. So if we look at the time axis, and this is the duration of all the calls, we can see suddenly that the call center opens at 10 a.m. and then there's this massive volume of calls. And we can see things like the average call duration, right? That's what this line is. Average wait time, average call duration, average call number of abandoned calls, and so on. And we can see like these are the long calls, for example. We also have data with relationships represented. So hierarchical relationships or relationships between data samples. Right, if you think of the London Underground map, that's a data set of the tube, right, or the London Underground. And every stop has some relationship with another stop, and that's how you get around, right? Typical visual designs include hierarchical networks or tree maps, right? And these get to be more complicated. This style of visualization is more complicated than some of the other ones. Right, here's an example of a hierarchical visualization. It's called a tree map. Right, it's from FinViz. So in this case, every rectangle represents a company that's traded on the New York Stock Exchange or something like that, or the NASDAQ. And the volume of the rectangle, or the area of the rectangle, represents the volume of trading on that day. And then the color is mapped to stock price. So if the price is going down, the color turns red. If the price is going up, the color turns green. Right? That's what this looks like in reality. Right? We can zoom in, but we can also hover the mouse to get more details. Now, what is the hierarchy here? There's a hierarchy encoded in this visual design. The stocks are grouped together, like all the technology stocks are grouped together in this rectangle. And then there's another rectangle called software, right? So all the software infrastructure stocks are grouped together. Computer electronics are grouped together. Semiconductor stocks are grouped together. So there's a hierarchy, like technology at the top level, then semiconductor at the next level, and then the individual companies at the next level. So it's a hierarchical relationship. And this arrangement is called a tree map. I think everybody has seen graphs before. Well, I know that you've all seen graphs before. Does everybody remember where we saw graphs before? Can anybody remember? We saw them on Friday from connectedpapers.com. Remember that exercise last Friday? Connectedpapers.com was a graph visualization, right? We saw that. So this shows the relationship between research papers. It's a graph, right? It's an interactive graph. You can hover your mouse over the different nodes and find out the details about the papers. You get the papers, the full details of the papers up in the top right here, right? And then of course we have interaction. Interaction is anything that the user can do to change what they're seeing. Maybe they want to focus in on a special stock, right? Maybe this is an interaction right here, using my mouse to focus on different stocks, for example, right? I want to see what the stock price of Amazon is. I want to see the details, for example, right? That's interaction. Zooming in and out is also a kind of interaction, right? So I can zoom in and out. Clicking could be an interaction as well. Okay, that is a short and rapid introduction to data visualization. It's a big topic. This is just to give you some introduction. And it's very useful for your dissertations when you want to study data. When you want to try to convince the reader that you've validated your hypothesis, or you've addressed the question, or you're trying to convince the reader that what you're saying is true as part of the evaluation in your dissertation. If you want to find out more, there are lots of resources. These are just two resources, right? This is a whole class dedicated for just data visualization, right? There's a playlist on YouTube. So if you want to watch, I don't know how many hours, maybe something like, I don't know, 20 or something hours of data visualization lectures, you can do that. This is another very valuable survey paper that's just talking about visualization resources, like what visualization resources are at your fingertips in terms of like reading, lectures, software, data, research papers, books, and all those sorts of things. Any questions about DataVis? It's a very fast introduction to the topic. I hope it wasn't too fast. Okay, so if there are no questions, we'll finish here. The workshop on Friday will be shockingly about data visualization. So we'll see you on Friday.